Today we're going to start section 2.5 out of our book. The title is The Fundamental Theorem of Algebra, which we'll talk about, but I added in there what we're really doing for this section is we're factoring and solving polynomials. That's our main goal for this section. So let's start off with a real important concept, something you learned way back early on in math. To factor and to solve a polynomial, they're different questions, but the way you do them is very similar. So basically, if you factor a polynomial, it's real easy to get the solutions from that. Or I said vice versa, if you have the solutions, it's real easy to turn them into factors. And that's why I said it's basically the same question. So let's start with a real simple example. If you're looking at a question and one of its factors is x minus 4, then the solution is x equals positive 4. In fact, we just used this concept when we were doing synthetic division. So basically, when you have just an x in your linear factor, all you have to do is change this sign here and you got the solution. Now, if you have a coefficient on the x, it's a tiny bit different. We still change the sign, and we still use the 2, but basically what you do is you change the sign, and then you put this number over this number. So if my factor was 3x plus 2, my answer would be negative 2 over 3, or negative 2/3. So those are some shortcuts for converting factors to solutions that you learned a long time ago. I want you to realize those also work backwards. So if I told you that we had some equation where a solution was x equals negative 5, then the factor would be x plus 5. And it works with fractions too. If I told you that we had a solution of x equals negative 7 over 4, then your factor, I'm going to leave a space but put the x in there. You're going to do it the same way. You're going to change the sign so it would be plus. The 7 goes here and the 4 goes there. So if your factor was 4x plus 7, the solution would be negative 7x plus 4. Just working that little shortcut backwards. So real important with what we're going to be doing for the rest of this section is realizing that if I ask you for solutions or factors, you can do either one and real quickly get the other from it. Now the next thing I want to mention is a vocabulary thing. There's actually a lot of different words that mean solutions. When we're talking about polynomials, I could ask you to solve it or find its solutions, which is basically the same question. Or I could ask you to find its roots, or I could ask you to find its zeros, or I could ask you to find its x-intercepts. Those are basically all the same question. So if you're asked to find any of those, you're basically being asked to solve the polynomial. And you can solve it by factoring, so you can group factoring in there too. So we have like 6 different ways I can word a question where I'm essentially asking you to do the same thing each time. So keeping that in mind, let's find the roots of this polynomial right here, or this equation right here. And again, I called it roots for this example, but I could have picked any of those words I just showed you. I could have said find the solutions, find the zeros, find the x-intercepts. I could have said solve for x. I'm asking you the same question no matter what. And this is actually a very easy question. It's like our first example from today. If I give you an equation that's already factored, you don't have to do any work. Just convert those factors into solutions. So I'm ready to answer this question. X equals, now I do get a 0. Anytime you factor an x by itself out, that gives you a solution of 0. I would have a negative 5 for the second one. I would have a positive 3 over 2 for the next one. And for my last one, I would have a negative 7 over 3. And that's it, we're done. So if the equation's already factored, it's simple. But basically our goal is going to be take polynomials and factor them so we can do this. So really, what our goal for this section is to take something that looks more like this. We have just an ordinary unfactored polynomial, and I just made one up. I threw some numbers in there. But if I gave you this and asked you to solve it, it's a little tougher. You don't just look at it and get the answers like our last one. So we're going to break this down into a few parts, this section. We're going to spend a little bit of time on it. And our main thing for the first part, what we want to do is we want to come up with a list of numbers that even might be a solution. Before we know whether they are or not, we want to come up with this list of numbers that might be a solution. And to do that, we're going to use what's called the rational zero test, which gives us a list of every possible rational number that even might be a solution to this polynomial. Now, a couple things to notice. We've seen the word rational twice. It's in the name, the rational zero test, and I said it in the bullet point above. Just a reminder, when I say rational number, I'm talking about whole numbers and fractions only. And what that means is if your polynomial has a solution that's either an irrational number, which would probably mean there's like a square root in it, or an imaginary or complex number like we just did in 2.4, then we have to find those a different way. Those aren't going to show up in the rational zero test. But the rational zero test will give us a list of numbers, rational numbers, that might be a solution to this polynomial. And that's the first step in solving. So here's how the rational zero test works. To make this list, you're going to make a list of fractions. We do get that plus or minus in the front. So we don't know whether our answer is going to be positive or negative. What we do is we're going to get a bunch of fractions and test both the positive and negative. But what we do is we take all the factors of the constant term, and when I say constant, it's the term that doesn't have an x in it, and we put those on the top of all of our different fractions, every combination. And on the bottom is the factors of the lead coefficient. And the phrase lead coefficient means the coefficient in front of the highest power of x. So if you have a 5th degree polynomial, it's the number in front of x to the 5th. Or if you have a 10th degree polynomial, it's the number in front of x to the 10th. Whatever that highest power of x is, you look there. So let's do a quick example of that. Let's find all the rational zeros, all the possible rational zeros of this. We're not going to find them yet. So basically, to do the rational zero test, I only need to look in two places. I need to look at the constant term, which is 10, and I need to look at the lead coefficient. So I scan through and I see that my highest power of x is x to the 5th, which means I'm going to use its coefficient. I'm going to use the 3 and the 10, and that's it. The numbers in between them, the 4x to the 4th and the negative x squared, you use those to find the actual zeros, but to find just the list of possible zeros has nothing to do with it. So basically my work could look something like this. I have the plus or minus. On top, I made a list of every possible factor or every number that divides evenly into 10, and there's 4 of them, 1, 2, 5, and 10. Then for the denominator, I take every number that divides into 3. Now that's easy, there's only 2 of them, 1 and 3. But that's not the answer the way it's written. That's kind of like that's notes, sort of, or a shorthand version. What you want to do is make every possible fraction out of those numbers with a plus or minus. So basically this would be my final answer. I said plus or minus 1, and that comes from putting 1 over 1. And then my next answer is plus or minus 1/3. That comes from putting the 1 over the 3. And then I repeat with every number on top. I have plus or minus 2. That comes from putting 2 over 1. And then plus or minus 2/3. That comes from putting 2 over 3. And then I won't keep circling, but I do the same thing with the 5 to get the 5 and the 5/3. I can do the same thing with the 10 to get the 10 and the 10/3. And then I'm done. So if you look at it, you actually have 16 possible answers there because we got 8 different fractions, or 8 different numbers, some of them aren't fractions, but you get a plus or minus on each one. So our list of possible rational zeros has 16 numbers for this one. Now as far as finding out which one actually are zeros, we'll work through for the rest of the week. So I want to talk about how to use the graph of a polynomial to get a few hints about like which ones from that list actually are solutions. So here's 2 important things. Number 1, every x-intercept is a solution. In fact, that was the very first thing I told you guys in the notes today. When we made that list of words that mean the same thing, I said a solution actually is an x-intercept. Now I did add a little bit to it. I said what it is a real solution. So it's a real number, not an imaginary, not complex or anything like that. Now, every term that does not cross the x-axis gives you two complex solutions. And let me draw a couple pictures real quick and show you exactly what I mean by that. So let's say I have a polynomial and it does this. It goes up, down, and back up. Now the 3 points where it crosses the graph, here, here, and here, are x-intercepts. They're real solutions. So whatever those numbers are, and I didn't mark the axis, but maybe it's like -5, -1, and +3 or something. So you get 3 real solutions. Now, if that graph did this, let's say it was very, very similar. It starts here, it goes up, down, but it never hits the axis and turns up again. So what you get is only the one real solution. Well, this shape of the graph right here, this part where it twists, where it goes down and back up, and like where, if you look at the first graph, where it really should have gone back and given you 2 more intercepts, but because it never hits the x-axis, that represents 2 complex solutions. So what you have on the left-hand side, you have a picture of a graph that has 3 real solutions. And on the right, you have a picture of a graph that has 1 real solution and 2 complex solutions. 3 solutions either way. I mean, there's still 3 answers to this question, but by knowing a little bit about the graph, you know what type of answers to expect. So here's a good thing for you guys to remember. The reason that the complex zeros come in 2s like that is because they come in conjugate pairs. And the word conjugate, I actually already went over with conjugates earlier this year with you guys, but I'll do it again. Basically, the idea is if an imaginary number is a solution, its conjugate automatically also is. And here's an example of that. So let's say in one question we realize that 3 minus 2i is a solution, or a 0, of our polynomial. Then without doing any more work, we automatically know that it's conjugate. And remember, this is what conjugate means. It's the same complex number, but with a different sign in the middle. So if 3 minus 2i is a solution, so is 3 plus 2i. Automatically, without you doing any work, you know that. So complex zeros always come in 2s. They always come in pairs. And they're always conjugates, each pair. So keeping that in mind, this is going to be our last example for today. We're going to kind of flip our first example from today backwards. So basically, in the first example, I gave you guys a factored polynomial, and I said, let's find the zeros. Well, for this one, I'm giving you the zeros, and we want to come up with the polynomial. So basically, what I want to do for this one, let's call our polynomial f of x. And what I said is, so these two numbers, 3 and 1 plus 2i, are our zeros. So the 3 is easy. If 3 is a 0, then x minus 3 is a factor. Now the 1 plus 2i is a little bit tricky. I'm going to draw out square brackets first, because what you actually have is x minus, and then in parentheses, 1 plus 2i. Now here's the important part though. Before I even wrote those two things down, what I should have done is realized, even though I didn't say it in the question, there's actually a third 0. Because if 1 plus 2i is a 0, so is 1 minus 2i. Conjugates always go together as solutions. So I'm actually going to have one more factor here, and it would be x minus 1 minus 2i. So if I kind of clean this up a little bit, what I get is x minus 3 times x minus 1 minus 2i, if I distribute that negative, and x minus 1 plus 2i, if I distribute that negative on the second one. So what I have now is I have a function f of x, but I'm not done with the question, because in the question I asked you guys to write a polynomial. And in factored form, technically it's not really a polynomial. Polynomial means like list out the terms from highest to lowest. X to the fifth plus 10x to the fourth plus dot 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 all the way to the end. So we need to multiply this all out. And we're going to do it in 2 steps. And one thing that you definitely want to remember, if you have conjugate pairs, always multiply those first. Like if you go in order, if I just try to do the x minus 3 times the x minus 1 minus 2i, I get this big, long, messy polynomial. And then I have to multiply that by x minus 1 plus 2i. If you multiply the ones with the conjugates, they clean up nicely. So let's do that. Let's leave the x minus 3 for now. And let's multiply this all out. I'm going to do basically distributive property 3 times. I'm going to do x times x is x squared. I'm doing this right now. X times negative 1 is negative x. And x times positive 2i is plus 2ix. And then I'll distribute the negative 1. I get negative x plus 1 and minus 2i. And then I should get 3 more terms when I do the negative 2i. I get negative 2ix. So I can squeeze it in. I get plus 2i. And I get minus 4i squared. I got it in. Good. Now what happens, because they're conjugates, all those I terms cancel out. Like I have a plus 2ix and a minus 2ix. And I have a minus 2i and a plus 2i. So this kind of cleans up nicely. We still have that x minus 3 out front. What we end up with is x squared. We have minus 2x total, because I have a minus x here and another one here. And then that minus 4i squared, remember I squared is negative 1, so that turns into a plus 4, which I combine with this plus 1 right here, and I get plus 5. So it looked like a mess. When I multiplied it out as this big, long, messy thing, but it turns into just an ordinary quadratic, x squared minus 2x plus 5. And now we can finish multiplying, and this part should be easier because there's no more i's in it. So if I multiply it all out one more time, I get x to the third minus 2x squared plus 5x, and I get minus 3x squared plus 6x and minus 15. So final answer here, we have an x cubed. Combine your like terms, we have minus 5x squared. We have plus 11x and minus 15. And that is a polynomial function that has the following zeros: 3, 1 plus 2i, and also, even though I didn't say it in the question, 1 minus 2i.